What's up, everybody? Welcome back. We have John Davidson from Fujitsu. Now, what John is going to do initially is we're going to walk through how we take cold air that's outside and turn that into heating inside when it comes to a heat pump, because a lot of people don't understand how we throw that energy around, how we move it around, right? One of the things John's going to talk about is getting that temperature of the outdoor coil really, really, really cold, colder than the outdoor temperature, so we can take heat from the outdoor temperature that's existing and apply it to the colder coil temperature. So basically we're pulling heat from the outside by having a coil that's a lot colder than the ambient. So it's the science behind how a heat pump works. We're just moving energy around, guys. So we got John Davidson. This is part one. This is the HVAC Know-It-All podcast. I'm your host, Gary McCreadie. This podcast is sponsored by Cool Air Products, Master, Cintas, and SupplyHouse.com. Go to the show notes and click on the links to check these guys out. All right, I don't think this is beating a dead horse, John, because anytime I get onto social media, there's a lot of people that still don't understand a heat pump that is designed for cold temperatures, cold climate, is able to do so. Obviously, we have capacity dips. That's just the way a heat pump works. As the temperature of the air starts to drop, we have less of a capacity or less capacity out of that heat pump. That's the way it works. And we can't do anything about that, really. I mean, I'm sure as technology advances, maybe 10, 15 years from now, our capacity drop won't happen until we hit super frigid, like minus 40, minus 50. Who knows how far this technology will go. But right now, I want to ask you a question. From Fujitsu's standpoint, how are we heating or extracting heat from the air and being efficient and having these high COPs of like 3-to-1, 4-to-1, or whatever it might be in these cold climates? How are we doing this?
So it's a great question, Gary, especially up here in the Northeast in the United States, where we do see some fairly cold winters and we are successfully heating homes and businesses using heat pumps. It comes down to just understanding the principles of refrigerant technology and how refrigerant works. A guy's way smarter than me figured this stuff out a long time ago. And then as technology's improved, we're able to extract and move energy more efficiently and better. I'm not an engineer and I'm not a scientist. The two foundational things that you've really got to understand, the old saying that heat rises, not necessarily. Hot air rises, but technically heat travels to cold. So that's kind of summed up in the second law of thermodynamics. Like I said, I'm not an engineer.
Can I stop you there? Because I want to make a visualization of what you just said. Because a lot of people think, yeah, heat rises, but it's not that heat rises, it's warm air rises. So the way I explained it to someone one time is if you have a tank of water and that water is at 70 degrees Fahrenheit, right? And then you come along with a jug of water that is at boiling 212 degrees Fahrenheit and you pour it in. Well, guess what? You're not going to see that water shoot to the top of the tank. You're going to see that water, if you look through a thermal camera, you're going to see that warm water disperse into the cold areas of the tank because it's trying to equalize itself. So I just want to give that visual, John.
Nature hates an imbalance. So if we think about heat like energy, you take an area of high energy and an area of low energy, nature just wants to find that balance. It wants to equalize that energy. And then a bunch of guys way smarter than me got to name these principles after themselves. So you've got Charles' Law, Ammon's Law, Boyle's Law, and those all come down to the second thing that we need to keep in mind. There's a correlation between temperature and pressure. As pressure goes up, temperature goes up. As temperature goes up, pressure goes up, and vice versa, right? So there's a correlation between those two things. If we think about the way the refrigerant works through the system, if I can increase the pressure of my refrigerant, I'm going to increase its temperature. I can then send that high temperature, high pressure refrigerant into some type of a heat exchanger. So in air conditioning, we send that high temperature, high pressure gas outdoors to our outdoor coil in the summer. And if I can get that outdoor coil hotter than the outdoor air, say I get that coil to 135, 140 degrees, then when that 95 or 100 degree summer air blows across it, that air feels cool to that coil. And the energy in the coil is going to move into that air. Now in the Northeast, we want to do the exact opposite. Rather than reject the heat outside in the winter, we want to reject that heat inside. We take a low temperature, low pressure vapor, we run it through a compressor, which compresses it. That increases the temperature and increases the pressure. We send that hot gas indoors. Now, if we can get our indoor coil hotter than our room air, right? So you get that indoor coil, 130, 135 degrees. You blow that 68-degree room air across the coil, the fan kicks on. Now that heat energy is going to move into the air, and we're going to move that energy into the room. And as we remove that energy, that high temperature, high pressure vapor is going to condense. In the old days, we used to call that a condenser for air conditioning, right? So now we're condensing that into a liquid. We send that liquid back out to our outdoor unit. And just like when we compressed it, the refrigerant, we increase the pressure and the temperature. When we release that pressure, we drop the temperature. And this is how we heat in the Northeast. We need to get that outdoor coil really cold. So if I can get my outdoor coil -20, -30 degrees Fahrenheit, then my 0-degree air feels warm. Now, it doesn't feel warm to us personally, but to that coil, it does.
I'm going to do another visualization here. Actually, this is more of like a 4D visualization because it includes actual senses. So I've done refrigeration work, and obviously being in Canada here, like I work outside and it's cold. So if I'm, let's say I'm working outside and it is, let's say it is minus negative, or it's negative degrees Fahrenheit, -5 degrees Fahrenheit. Okay. But then I come inside and I go into refrigerated box that is +5 degrees Fahrenheit. Even though that's cold to someone that might be in a room temperature room, like an office, to me, it's warm because I'm coming in out of that negative temperature and I'm going into a 5-degree box, right? So that's sort of like a correlation to what you're saying. It, like you said, it might feel cold outside, but to that coil, that's actually feeling a lot warmer as it's drawing in that cold air from outside, because the coil temperature is below. That's the only way we're going to absorb that energy from the air.
A good analogy is that most people can relate to is walking up and down the aisles of a supermarket. Now, the entire supermarket's all in temperature, right? As you walk up and down the aisles, when you get to the frozen food section, it's physically the same temperature in that section, but you feel colder because your heat energy from your body is being absorbed by those coolers, any of those open air coolers. So although it's the same temperature, you're seeing that transfer of energy from your body into that cooler. So we're just moving energy.
That's all we're doing. Yeah, we're just moving energy from one place to another.
And there's any number of different refrigerants that we could use. And you start getting into the environmental impacts of how refrigerant works and their thermodynamic properties. And so the industry is constantly looking for a better refrigerant that moves energy, but is also less harmful to the environment. And so we're seeing that transition in the industry right now from refrigerants.
The inverter technology that allows a compressor to ramp up and down and load match the indoor conditions is a very valuable tool as compared to a one-speed compressor. Can we talk about that for a minute?
In the old days, when air conditioning started becoming popular in homes, your compressor was either on or off. And then when we started doing heat pumps, if anybody remembers the old refrigerant, the R22 stuff, you would use a heat pump, but we really didn't sell those once it got below 40-degree ambient. They just weren't, they couldn't produce enough heat. The compressor would run, it would generate heat, and then it would need to rest. And you'd lose all the heat out of the house. So the thought was heat pumps just don't work in the Northeast or up in Canada. But that's because it was either a single stage or a two-stage. It was either on or off. With the inverter technology now, we have the ability to vary the speed of our compressor in order to match that load. So it's kind of like running cruise control in your car. You set the cruise control to 65 miles an hour. As you come up to a hill, the load increases, your engine increases, and you maintain that speed. And that's what we're able to do with the inverter technology. So we're just kind of riding that fine line as the load changes, or as we need more energy in or out of the room. Our compressor has the ability to speed up or slow down.
I do have a question, because I know that I worked with a local company here, Foundry Mechanical / Foundry Heat Pumps, and we went on into an install that we covered with a Fujitsu heat pump / air handler. It wasn't a dual fuel. It was an actual air handler with the auxiliary heat strips in it, the resistive heat. Now, this was an XLT. Now, I'd like to ask you about this because I want to know how we increase the capacity of the machine when we get colder outside between different models of equipment. So the XLT, from what I understand, is can work down to 100% capacity at -15 degrees Fahrenheit. You can correct me if I'm wrong here. And then the XLT Plus down to -22 degrees Fahrenheit at 100% capacity. Is that right?
We're not quite 100% capacity.
Not quite
We're
100%?
about 100% at -5, and
Okay.
then we begin to drop off
Okay.
a little bit.
Okay.
So we recommend contractors look at the capacity tables in the design manuals. When you look at a catalog is going to give you AHR rating, and it's going to tell you it's good from this to this, and that's based on their testing. And AHR considers lower ambient heat to be 17 degrees ambient. NEAP has certified a lower ambient heat pump, which is 100% of its rated capacity at 5 degrees. When you start getting below that, like we mentioned, when you get into those really cold temperatures, there's less energy available for us to use. We can still harvest that energy, but you're not still getting that 100% capacity. It begins to tail off.
That's 7 degrees between the XLTH and the XLTH Plus. How are we accomplishing the additional capacity out of that one?
It's through management of the refrigerant flow, the amount of refrigerant, the coils, our ability to transfer energy. And then there are some things that need to get added in to allow the system to work. So you'll find that they change the printed circuit boards that are in there need to be designed to work in those much colder temperatures outdoors. The wiring actually has to change. The little plastic Molex connectors change. And they add a base pan heater to allow that unit to defrost. And depending on your manufacturer and your AHR rating, you want to find a manufacturer that is getting their AHR rating with the base pan heater installed, rather than one where it becomes a field installed option and isn't part of the actual rating. Because then you're not getting the efficiency that you're expecting.
Okay, so let's talk about that base pan heater for a minute, because I actually, going back a couple of years ago, I actually had to go out and install base pan heaters after the fact in a bunch of heat pumps that were installed in this motel. It was like a classier, it wasn't like a murder motel or anything. It was more of like a nicer upper class type motel in ski area near Collingwood, Ontario. But it was they didn't have pan heaters. So what would happen when it went into defrost is the ice would build up in the pan, because in defrost that ice is melting, turning the water, it's hitting the pan and it's freezing again. And what it would do is it would block the fan from turning, like the outdoor fan from turning. It would also that ice would push the coil. It would like build and bulge and then push the coil out, which is not a good thing. So I went back after the fact.
Distinct crush mark.
Yeah, for sure. So I had to go back after the fact and install these base pan heaters. So what you're saying is 100%, right? So with that base pan heater, for the audience listening, as that ice starts to melt, the water drips down into the pan. That base pan heater will allow it prevent it from freezing and drip like outside the unit in the drain holes in the unit, right? That's how it works, right, John?
We talked about the ability to absorb heat, energy in 0, -5, -10 degree air. Well, by running our outdoor coil colder than the ambient air, we're eventually going to drop below dew point. And that's when any moisture that's in the air is going to begin to condense and freeze on that coil. And as it does, it begins to build up. It restricts airflow. We need to defrost that coil. That's where our defrost mode and baseband heater work together. It thaws that coil to allow air to move over that coil so we can absorb the energy. But that defrost, that water, once it melts, has to go somewhere. So the baseband heater prevents it from freezing in the bottom of that pan and crushing the coil, causing leaks. But it's important for installers to understand and to think about, where's that water going to go? So a grid installation, you're going to have that outdoor unit raised up so that when it goes into defrost, that water can drain down and away from the unit. It means owners need to understand that they need to keep the snow clear from under that unit, whether you're using a 12-inch stand or an 18-inch stand. If you're in an area where it gets cold and snowy, you got to keep that clear so that water can then drain away somewhere where it's not going to cause problems and issues related to other parts of the building or the structure.
Yeah, no, for sure. No, it was a good point that you brought up. So as far as the heat pump goes and the indoor air, the air handler itself, I know dual fuel. A lot of people love dual fuel. I want to get your opinion on this. Dual fuel versus an actual air handler, matching air handler with resistive heat strips. Do you want to talk about those specifically and the differences and advantages, disadvantages?
Absolutely. I think we need to have a conversation with contractors, homeowners, customers, and end users about why they're considering this technology. What's motivating this? And, depending on where you live and your personal feelings, you may want to get off of oil, fossil fuels altogether. And that's great. We see a lot of customers are moving to this technology because they feel that it's greener, it's cleaner, less dependent on fossil fuels. And so we can do that. Others are looking at it through incentives. Well, because there's money available. And then others, it's price is the driving factor, economic. So you have to look at really what's the motivating factor behind why somebody's interested in using a heat pump. So that helps you to understand how to design and to lay out a system, whether you want to go 100% electric and you've got a passive house that requires very little energy to heat and cool, or you've got an older home that you're trying to retrofit, but you still need to be able to maintain heat in colder climates. So every system is going to have what's called an economic balance point. And it really comes down to what's the cost of a BTU. So there is a cost associated with running a heat pump. And there's a cost associated with burning oil, burning gas, burning propane. So if economics is the driving factor, there's a point at which it will be more cost effective from a dollar's point of view to run a second type of fuel. And that comes down to what's your cost for your fossil fuel and what's your cost for electricity.
All right. So it comes down to a lot of factors, like you're saying, and some people choose to go with dual fuel because maybe where they live, gas might be cheaper than electrical once you get into these really colder temperatures, which is totally understandable. But there is an advantage when you use a matched air handler over a dual fuel for the actual efficiency of that system. Because usually when you have a heat pump paired with its own air handler, it's communicating. So the compressor and the fan are going to ramp up and down together, where if you're using a furnace, maybe it's not even an ECM motor. Maybe it's not going to communicate with the outdoor unit, so they don't know what each other are doing because they're not talking to each other. So maybe talk about some of the advantages you do have with a matched air handler on a communicating system.
So when you look at a communicating type system, like you said, your compressor and your fan are going to communicate and work with each other. In order to move energy in the form of heat, either in a building or out of a building, two things are absolutely required. You've got to be able to move the refrigerant, which is why the installation of the refrigeration piping is critical, and the insulation of it. And you've got to be able to move air. We've got to keep the coil clean in order to get air, in order to get that efficient energy transfer. In an inverter-driven system, what's going to happen is as the load increases, your compressor is going to speed up, your expansion valve is going to open, and it's going to allow more refrigerant into that coil, and then your fan speed is going to increase. You're going to increase your capacity. As you get closer to whatever your set point is, your expansion valve is going to begin to close down. Your fan is now going to begin to close down, and your compressor is going to slow down. And it's really like we used the analogy earlier of cruise control. You're going to ride that curve, and the compressor, the fan, and the expansion valve are all going to work in unison using the integrated software program that's going to monitor how everything is working together and the energy efficiency. So the closer you get to set point, the slower things are going to be operating. It allows you to maintain your set point temp without necessarily overshooting or undershooting. Gives you much more precise control over those temperatures and over comfort within the space, as opposed to a non-communicating system where you're going to be working basically off pressures on the outlet of the coil. Your fan's going to be on or off, or maybe it's a 3-stage type fan. You may ramp up until you hit set point, and then your compressor is just going to ramp right down. It's not going to ride that curve you would with a communicating system.
All right. Now, with communicating, what are we monitoring? Obviously, indoor temperature, outdoor temperature, anything else, return air temperature, supply air temperature.
So depending on the system that you have, the level of system that you purchase, you're going to be looking at your incoming and outgoing refrigerant pipe temperatures. In the case of heat, what is my hot gas coming in? What is my temperature of my liquid coming out? And you're going to be monitoring your incoming and possibly your discharge air temperature. On the compressor side, you're going to be looking at the temperature of the shell of the compressor. How hot is my compressor? What's my hot gas discharge temperature coming off of that compressor? As well as your ambient air. And then you're also looking at the set point. So the printed circuit board, the software in there is looking at what is my deviation from set point. And on a single zone system, that's just 1 point. You've got a multi-zone system. Now you're looking at the accumulation of each room. What's my set point? What's my deviation? How far am I from that? And that's going to dictate to the compressor how much refrigerant it needs to send out to match that load in each area.